All right, so let's go through the solution. So here I've written as if I only had 2 points, point 1 and point n, with a whole bunch of points in the middle. Okay, so I've got the matrix A times m equals 0. How big is the matrix A? Well, it's 12 across, right, because there are 12 m's. And how many rows does it have? Well, it has 2 times n, where n is the number of points. So it's a 2n by 12 matrix. M is just an m by 1 vector, and here's the 0 vector of length 2n. Okay? So now let's talk about solving that. One step at a time here. All right, so here's our goal, right? We said we want a unit vector that minimizes am, a unit vector for m that minimizes am. So let's do what's called a singular value decomposition, and I'm going to assume that you've seen that before, at least someplace, but the idea is that any matrix can be decomposed into this UD V transpose format where V is a real orthogonal matrix. So in our case, it would probably be a 12 by 12. U is going to be a much bigger matrix. It says orthogonal, but I should be more precise. Each column is orthogonal to each other, so that would be, in this case, a 2n by 12. And most importantly, D is a diagonal matrix, so it only has values on the diagonal, and it is customary to write it as in decreasing order of absolute value, so from the biggest D to the smallest, all right? So we're going to write A is equal to U dV transpose. So minimizing AM is the same thing as minimizing U dV transpose M. Got it? So far nothing significant other than you have to use your singular value decomposition code from MATLAB. Here comes the first little bit tricky part. That is that the magnitude of U dV transpose M is equal to the magnitude of just dV transpose M. Why? Well, these are just unit vectors, right? The U's and V also, for that matter, are made up of orthogonal unit vectors. So multiplying them doesn't change the magnitude of the matrix. And that's why these magnitudes are the same. And it's also why the magnitude of M is equal to the magnitude of V transpose M. For those of you who think about such things, V in this particular case is a orthogonal, in this case 12 by 12 matrix. You can think of it as like a rotation matrix. So when you rotate a vector, you don't change its magnitude. So the magnitude of M is the same as the magnitude of V transpose M. So that means instead of minimizing U dV transpose M, we can just minimize dV transpose M, subject to, instead of being subject to M equals 1, subject to V transpose M equals 1. Got it?